Something interesting is happening. A new study suggests the Earth and Milky Way are surrounded by something huge, 2 billion light-years wide. For decades, scientists believed that on large enough scales, the universe is uniform, the same in every direction, with galaxies scattered evenly across the cosmic web. It's a principle called cosmic homogeneity, and it's been the foundation of modern cosmology. But a bold new theory suggests we may need to rethink that assumption. What if Earth and the entire Milky Way are located inside a giant cosmic void, a region of space so vast, so empty, that it spans nearly 2 billion light-years across? According to recent research, this isn't just a speculative idea. It could explain one of the most troubling mysteries in cosmology, the Hubble Tension, the growing mismatch between how fast the universe is expanding now versus how fast it was expanding in the early universe. If true, this void would be one of the largest and most significant structures ever discovered. And it would mean that our location in the cosmos is far more unusual than we thought. This video takes you deep into the heart of that possibility, how it emerged, what evidence supports it, and why it could change the way we view our place in the universe forever. To understand this theory, we have to start with the structure of the universe. Imagine the cosmos as a vast, three-dimensional web, a cosmic sponge, with galaxies clumped into filaments and walls, and massive empty pockets in between. These empty pockets are called cosmic voids, regions that contain far fewer galaxies, matter, and dark matter than average. Cosmic voids aren't rare. In fact, they make up most of the volume of the universe. But they're usually modest in size, between 30 to 300 million light-years across. These voids are surrounded by denser areas called galaxy clusters, where matter has gathered over billions of years due to gravity. So, as the universe evolved, matter fell into these denser zones, leaving behind vast, underdense regions. But in the last 2 decades, scientists began noticing something odd about the space immediately around us. It didn't seem normal. Some astronomers suggested that our galaxy, the Milky Way, might actually reside inside a much larger void than expected, a supervoid with drastically lower matter density. This isn't just theoretical. Observations of galaxy distribution suggest that locally, there might be significantly fewer galaxies than average, hinting that we may be sitting inside a gigantic cosmic bubble. In 2013, a team of astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, analyzed the distribution of galaxies in the local universe using data from galaxy surveys. What they found was surprising. They noticed that, compared to more distant regions, our local area seemed to have fewer galaxies and less matter than expected. They proposed that we might be located in what they called the KBC void, a vast, underdense region nearly 1.8 billion light-years in diameter. Others referred to it as the local hole, a cosmic zone where the density of matter is as much as 20 to 30% lower than the cosmic average. Why does this matter? Because the density of matter affects how fast the universe appears to expand around us. If we're in a low-density region, galaxies nearby would be pulled outward faster, not because the universe is expanding more quickly in reality, but because of the gravitational imbalance created by the surrounding structure. This means that local measurements of cosmic expansion could be biased by our position, and we might be seeing the universe's behavior through a distorted lens. But this idea remained controversial until recently. To fully appreciate why the void idea matters, we need to understand the Hubble tension. The Hubble constant is the number astronomers use to describe how fast the universe is expanding. But there's a problem, and it's not small. There are 2 main ways scientists measure the Hubble constant. Local measurements, using Cepheid variable stars and type Ia supernovae to calculate distances to nearby galaxies. These suggest the universe is expanding at around 73 kilometers per second per megaparsec. Early universe measurements, based on the cosmic microwave background, the radiation left over from the Big Bang, as observed by satellites like Planck. These suggest a slower rate, about 67 kilometers per second per megaparsec. That's a discrepancy of nearly 10%, far beyond the margin of error. This has become one of the hottest debated issues in cosmology. Why would local measurements show a faster expansion? Enter the void theory. If we're in a massive underdense region, then galaxies around us would appear to move away faster than they would if the universe were perfectly homogeneous. This would inflate our local Hubble constant. The theory doesn't eliminate the tension entirely, but it could explain a large part of the mismatch without inventing new physics or modifying the standard model of cosmology. But how do you test for a void that enormous? One of the most powerful tools to test large-scale cosmic structure is baryon acoustic oscillations, or BAOs. These are ancient sound waves, ripples left over from the early universe, frozen in place as galaxies formed. They provide a kind of cosmic ruler that astronomers can use to measure distances across space. In mid-2025, Dr. Indranil Banik and Vasileios Kalaitsidis from the University of St. Andrews published a new study analyzing BAO measurements spanning 20 years. They presented their findings at the Royal Astronomical Society's National Astronomy meeting. What they found was remarkable. The best fit to the BAO data occurred when the model included a large cosmic void centered around the Milky Way. The size? Roughly 1 billion light-years in radius, or nearly 2 billion light-years across, and the density around 20% below average. If these results hold, it means that the echoes of the Big Bang are subtly reflecting the structure of the void we're inside, that the very fabric of space is whispering to us that we're in an unusual place. It doesn't just help with the Hubble tension, it suggests that our cosmic position may be far more unique than previously thought. If the void is real, and if we really are drifting inside it, then it challenges one of the oldest and most sacred ideas in cosmology, the Copernican principle, which says Earth doesn't occupy a special or privileged place in the universe. Modern cosmology rests on the idea that the universe is isotropic and homogeneous, the same everywhere and in every direction, at least on large scales. But if we're inside a massive underdense region, then we are, in a very real sense, in a special location, a region unlike most of the rest of the observable universe. And if the expansion of space appears faster here because of that underdensity, then many of our local measurements might be skewed, not incorrect, but shaped by where we're standing. This would force scientists to recalibrate how we interpret redshifts, distances, and cosmic acceleration, potentially even affecting how we think about dark energy and the ultimate fate of the universe. But not everyone is convinced. Many scientists are skeptical of the void hypothesis, and for good reason. The standard model of cosmology, the lambda cold dark matter model, assumes that large enough regions of the universe average out. In other words, voids exist, but they shouldn't affect cosmology at billion light-year scales. Some studies using other data, like supernova surveys or gravitational lensing, don't see evidence for a void that large or that deep. Critics also point out that the void hypothesis requires us to be very close to the center of the underdense region for the expansion to appear uniform in all directions. That's statistically unlikely. In essence, they say, yes, the idea is elegant, but is it probable? Others argue that the Hubble tension likely needs new physics, perhaps a new type of particle or changes to dark energy behavior, rather than just a geometric trick. Still, the void model is gaining interest, especially because it doesn't require rewriting fundamental physics, just rethinking where we happen to be standing. This theory is far from settled, but the tools to test it are already here. Upcoming surveys from missions like Euclid, the Nancy Grace Roman Space Telescope, and the Vera Rubin Observatory will provide deeper, more precise maps of galaxies and cosmic structure than ever before. These data will allow astronomers to precisely measure galaxy densities over larger distances, track the motion of galaxy clusters affected by underdense regions, use gravitational lensing to detect mass distribution directly, and apply kinematic Sunyaev-Zeldovich effects to map motion in the cosmic microwave background. If these measurements confirm the existence of a 2 billion light-year void around the Milky Way, it will be one of the most profound discoveries in cosmology. And if they rule it out, it will help sharpen the focus on other possible solutions to the Hubble tension. Either way, the universe is giving us clues, and we're finally listening closely enough to hear them. So what does it mean if we really are inside a void? It means we've been measuring the cosmos from inside a bubble. It means the expansion of the universe might look faster not because it is, but because of where we're watching it from. And it means that in the grand puzzle of the universe, our place in it may be a cosmic coincidence or a clue. The idea that Earth and the Milky Way are drifting inside a massive, empty zone of the universe once sounded like science fiction. But today, it's a live question at the frontier of astrophysics, one that combines galaxy maps, ancient sound waves, and the very structure of the universe. Are we in a void, or is the void in our understanding? The answer is not 100% clear, but the universe is still mysterious, and the more we look at it, the stranger it becomes. Thank you so much guys for watching, and make sure to subscribe and turn on notifications for more explorative and interesting videos in the future.